In this problem, a car is traveling at a constant velocity of 10 meters per second. The problem gives us an initial position for the car of 100 meters. We're asked to plot the acceleration versus time and the velocity versus time. Later, we'll plot the position versus time too. So there's a reason that the graphs have been stacked in this order. We like to put the original function on top, which is going to be the position. And then we're going to put what is called the first derivative underneath that. That's the velocity function, of course. And what we're going to do with the acceleration is that's going to be the derivative of the derivative. It's called a second derivative. And all the same rules we use to turn an original function into a first derivative, we'll use those same rules to turn the first derivative into the second derivative. All right, so let's see how this one works. First thing we can do is just plot some of the given information. They say that it's going to travel at a constant velocity of plus 10, which means that the velocity is going to stay 10 throughout time. It's not going to change. So we need a horizontal line for that. Okay, we're also told that this car starts off at a position of 100 meters. So that would be this point here. And now, since we're being asked to plot the acceleration, we just need a derivative of the velocity. So what's the derivative of a constant 10? I'll write it down here. A equals dv over dt. Take the derivative of 10 and you get 0. There's actually no acceleration in this problem. When an object travels with constant velocity, there's no change in the velocity with time. But acceleration is defined as a change in velocity with time. So here we have no acceleration. All right, let's look at number 2 now. 2 says, for this question, let t equals 0 be the initial time, and choose a final time of t equals 10 seconds. We want to shade the area underneath the velocity curve between t equals 0 and t equals 10. The signed area under the curve will be equal to the displacement of the car from t equals 0 to 10. So let's shade that area. All right, now we're supposed to use the area of a rectangle formula to find the displacement of the car. So let's take a look at the dimensions of that rectangle. It's got a width and a height. Now the height is given by v, the velocity. And the width is given by some change in time, delta t. So it was Sir Isaac Newton, famous physicist and mathematician, who discovered the relationship between these graphs. And he discovered the mathematics of calculus to describe them as well. His great insight was that if we were to multiply a velocity times a time, then the area under that curve would have meaning. It would be the displacement of the object. And so there's a formula in physics for this which says delta x equals v times t. And if we can just multiply those two things, then we'll know how far the car has traveled. So let's go ahead and plug in the numbers now. It's a 10 meter per second speed, and it lasted for 10 seconds. So how far did the car travel? 100 meters. Now this delta x is neither an initial nor final position. It's a change in the position. It's a change in the graph above. So in our graph above, we started off with an initial position of 100. And then from there has to be an addition of another 100. And by 10 seconds later, we'll now be located at this new position, which is called x final. The formula for figuring out how you get from the initial to the final is xi plus delta x equals xf. An initial value plus a change equals the final value. One of the most fundamental formulas in science and math. So we're going to start off with 100 meters initially. That's where we're located. We found through the mathematics above that we were going to have a displacement or change of 100. And that takes us to 200. And that's our final location. We also want to do this with an integration. So let's go ahead and try the definite integral from 0 to 10 of the velocity function dt. We have to find the antiderivative of 10, which would be 10t. And then we just want to integrate from 0 to 10. And so that's going to give us 10 times 10 minus 10 times 0, which is again 100 meters. So both the algebra approach and the calculus approach both worked here. Now, this formula here is a rewriting of the formula that I had showed in the middle. It just says delta x equals xf minus xi. 200 meters minus 100 meters equals 100 meters of change. What we'd like to do next is put different positions of the car into a table so that we'll know where the car is located at different times. The x is position, whereas delta x is displacement. We start off at 100 meters. And displacement is all about change. And so since no time has passed yet, there hasn't been a change in position yet at t equals 0. Since we're going 10 meters per second, how far have we traveled after 2 seconds have passed? After 2 seconds, we've traveled 20 meters. So where are we located now? 120 meters. And we want to draw a dot that shows that. After 4 seconds, we've traveled a total of 40 meters from our initial position. That's the change, though. X is where we're located relative to the 0 of the coordinate system. That would be 140. And the pattern keeps going like this. until we can draw the graph. Clearly, the graph makes a nice linear function. What we want to do next is come up with linear equations that fit these values. An equation for the displacement of the car could be delta x equals v times t, which is 10t. Now, how can we use calculus to find this same equation? We want to use an integral, but we want to be very clear about what it is we're doing. So what will our interval be? We'll go from 0 to some final time, tf. We want our limits to be from 0 to tf. And we want to do this on the function 10 dt. Then what we'll do is we'll use the fundamental theorem. And we'll evaluate from 0 to tf. And that's going to be 10 tf minus 0, which is 10 tf. We get the same formula as before. But now let's find an equation for the position of the car. That's not delta x, that's x. And this time, we're not going to do a definite integral. We're going to do an indefinite integral. So 10's antiderivative will be 10t. And this time we'll put a plus xi. So what is that initial position? That came from the givens in the problem. It's going to be 100. And there we go. We created a formula which will give us the values in this table.